afternoon. It's my pleasure to introduce our Progress Energy Distinguished Technical Lecturer, Professor Arthur Motten, who I have honor to know for more than 20 years. We work together at Penn State, and here we have a lobby from Penn State, which will cheer for Arthur.
Thank you. Appreciate that. I need all the help I can get.
So Arthur is the chair of nuclear engineering program and professor of nuclear engineering and material science engineering at Penn State University. He holds a degree in mechanical engineering and nuclear engineering from Federal University of Rio de Janeiro, Brazil, and PhD in nuclear engineering from University of California. Before joining the Penn State faculty, and that happened in 1992, and I show up in 1993.
That's right.
He worked as a research associate in the CAA, which is the national lab in France, at the Center of Nuclear Studies in Grenoble, France, and 2 years as a postdoctoral fellow in the lab in Chalk River in Canada. Professor Motten works in the area of radiation damage and environmental degradation to material, with specific emphasis on cyclical alloys, with current project in the areas mechanical testing, corrosion, and radiation damage. He has special interest in using advanced characterization techniques such as X-ray scattering from cyclotron radiation sources, vision electron microscopy, radiation, fundamental mechanism of corrosion and radiation damage. Professor Motten is a fellow of American Nuclear Society, and in 2015 he received the Mishima Award from the ANS for outstanding contribution in the research and development work on nuclear theory materials. In 2016 he was awarded the ASTM William Crowe Medal for sustained impactful contributions to zirconium metallurgy, including corrosion, writing, mechanical property, and radiation. He is current chair of the Nuclear Engineering Department Organization. Please join me in welcoming Dr. Motten.
So thank you, Custodin, for this introduction. This is the title of my talk, Hydrogen and Zirconium Alloy Nuclear Fuel Cladding, and it's a presentation that I have many different interests: corrosion, radiation damage, and this is one of the most important of all, I think. So this is the outline of my talk. I'm going to give you a little bit of an introduction to nuclear engineering at Penn State. There are many things happening there that I'd like to update you on, but also then talk about nuclear power in general, why we're doing this stuff, why do we want to make fuel work harder for us and get better results, but what are the challenges of it. And then hydrogen behavior is going to be the main part of my talk. And there's 4 parts, I would say, for hydrogen behavior. There's hydrogen pickup, during corrosion. There's hydrogen transport and redistribution inside the material. And then the part I'm going to be talking about mostly is hydride precipitation and dissolution, and the formation of mesoscale hydride microstructures. And then the effect of these hydrides and these particles on the mechanical properties of the cladding, and then have some conclusions. So this work is done by me, but also by a lot of my former students, many of you that you know. So then they all have gone on to do bigger and better things. Evra is about to leave and go to Arriva. Pierre Clement is still working there, but I have a bunch of collaborators, John Almer, that I think some of you guys have worked with, Mike Tonks, Mark Damon, and Don Koss. And this research was funded by the NRC, by NSF, by DOE and UP, and by the music program, which has nothing to do with music, but it's mechanistic understandings of zircaloy corrosion. When I presented this talk to my students, they said, "Where's our picture?" So here it is. This is the current crop of students. And the 2 that have contributed the most to this is Pierre Clement here and Evra, who is here. So the Nuclear Engineering Department in Penn State was established a long time ago, 1959. The reactor has been operational since 1955, although we changed the reactor in 1965 from a materials testing reactor to a trigger-type reactor. The department was founded in I would say that our nuclear reactor radiation science, the top nuclear research facilities in the country, is very well run by Kananulu. We have a very large undergraduate class. We have, if you count all the BS in nuclear engineering in the country the last 7 years, over 12% of those have come from Penn State. So we have a large undergraduate population, but at the same time, we're still graduating a lot of graduate students. And we have a very active online program, I think as you guys have as well. But we have many students, and since 2001, we have graduated over 180 students. Our focus has been traditionally on nuclear power and reactor physics, thermohydraulics, materials controls, but we also have nuclear security and radiation detection. Now, and I want to say, Kostadin and Sherry alluded to the number of Penn Staters that we have here. And I want to take responsibility for all the success that you guys have, you know, with Kostadin, Maria, and Yusri, and Jason, and everybody else that had Jamel, that was here at Penn State. And but we got some of yours back because our dean now comes from, or was formerly here, the former department head in material science, Justin Schwartz. So this is where we currently are, and you can see it here. It's the Reaver building right there. We are going to move across the way to this building, Hallowell, around here somewhere, and this is going to happen on July 1st. So as of July 1st, this is what's going to happen. A new department. We're going to separate the Department of Mechanical and Nuclear Engineering into the Department of Mechanical and the Department of Nuclear Engineering. Our current faculty is going to increase to about 15 full-time equivalent faculty, so we're going to be hiring a lot of people over the next few years. We have a national search for a department head, and yes, because I don't want to be a department head, stuff. The other thing that I want to say is we have an alum at Penn State that developed his technique for creating borated inserts for wet storage, and made a major gift for us. So as of July 1st, will be the Ken and Mary Alice Lindquist Department of Nuclear Engineering, the first named Department of Nuclear Engineering that I know of in the country. We have a new website where all this is, and that's right here. So I encourage you to take a look at it and learn things about us. The Penn State Brazil reactor, I just went through your reactor, which is very impressive as well. We have some unique capabilities. We have this moving bridge that can translate XY and then rotate as well. So we can take the reactor core to particular beam ports that we want. And it's used a lot for research and for education. What's shown here is the president of the country, Dwight Eisenhower, along with his brother, who was at the time the president of Penn State, Milton Eisenhower, and the dean of engineering. And this is Milton Brazil, who actually designed the reactor. They're actually looking at an empty space there because the core was not there, but that's a nice picture, right? So we have a bunch of things in there. They have this reactor bridge that I talked about. They have a radiochemistry laboratory and the nuclear security laboratory that was funded by a grant from DOE. Reactor Control Council. As you do as well, we train many of our students as senior reactor operators, and they come up with that training. And we have a very extensive use of the reactor facility for nuclear laboratories. I'm showing here materials because that's what I'm interested in, right? But the Millennium Science Complex, it's where the Material Research Institute is. It's this very futuristic-looking building here, which has two wings. One wing here, one wing here. One is for materials, the other one is for life sciences, and in the middle, you have the characterization facilities, which include, from my interest, they include the transmission electron microscopes. We have a TechNI, a Talos, and a couple of FIBs. We also have a very strong effort on materials computing. We have many faculty that have interest in this area, both in materials and in nuclear. And they have very, they do computations at very different scales. You probably know, some of you who are in materials know the department head there, Susan Sinnott, but they also have Lunkin Chen, Zikui Liu, many different people that do a lot of materials computing. And then we have this nanofabrication facility that is very useful for many different things. So our nuclear engineering research at Penn State is focused on many areas here, and at steady state we expect to have, for now, with the faculty we have, about 50 grad students, but the faculty will grow to about 15 from the current 8. So we're going to need qualified grad students. So I understand that most of you are already grad students, but if there are undergrads that would like to then apply to Penn State, we do, so just send me an email at here at itm2@psu.edu and let me know. We're very interested in having, cross collaboration between different universities, having Penn State students come to NC State, having your students come to our place. I think it's always a good idea to change schools so that you see how things are done in a different place. So we're also doing faculty searches, and we have a faculty search going on right now, but we're doing a department head search, and that's what a part of the establishing this new department is doing this national search, and that's a little bit behind this search here, but it's ongoing, and we're going to do more searches over the next few years. So if some of you are postdocs and are thinking about a faculty position, that keep us in mind. Nuclear electricity, I know I'm preaching to the choir here, but it provides 11% of the world's electricity, and a country like France, for example, that has 75% of their electricity from nuclear power has a very small carbon footprint. They are trying to increase it now by decreasing the amount of nuclear power. But in the US as well, if you want to not have a lot of carbon emissions, there's not really any other way to do but to keep the nuclear power plants going because of the intermittency of the renewables and all that. So, but it's still one of it's likely the major contributor to carbon-free electricity. We did publish a textbook that some of you are aware about. This is my former research advisor, Donald Lander at Berkeley. And we worked on the fundamentals, and this textbook is for the nuclear materials class. It talks about crystallography, point deflection, so all the basics that I always say that I was talking to KL, that we have to teach material science to the nuclear engineers and nuclear engineering to the material scientists. And this is the teaching of the material sciences to the nuclear engineers. And then right here we start talking about interactions of particles with matter. But we're working on the volume 2, which is more the applications, and that will include oxide fuels, zirconium alloys, reactor chemistry, hydride fuel failure, intergranular stress corrosion cracking, hydriding, hardening and brittlement, growth, creep, and severe accidents. So that's coming. So why do we try to, we're trying to keep the fuel longer. We're trying to keep it maybe at hotter temperatures in the light water reactors. That's what they call more severe fuel duty. They have to stay longer, they have to stay hotter, and then they have to stay with less failures. Right? Understand how, and one of the limiting factors that we have is the amount of hydrogen that the material takes in, and I'm going to talk about that. So just the basics here, and many of you have seen these pictures before from Westinghouse and all, but you have the fuel bundles here. We have this reaction, Zr plus H2O going to ZrO2 plus H2. This obviously is a chemical reaction that increases exponentially with temperature. So in the Fukushima accident, this went very fast, and therefore generated a lot of hydrogen, which then mixed with the oxygen in the buildings caused the explosions that you saw on YouTube, right? So what happens is you form this layer of oxide here, which is adherent to the oxide and limits further reaction. And the amount of hydrogen that is generated here, a fraction of that gets into the clad. And that's the fraction that we are concerned about. So that's the fraction, the hydrogen pickup fraction, and that's the hydrogen absorbed over the hydrogen generated. It's on the order of 10 to 15%. But it varies during corrosion, and it varies with the type of alloy. we have a new a model that kind of addresses this, and that's from the thesis of Adrien Coué, who is now a professor at Wisconsin. I think it was a very good advance at the time, but that's not what I'm going to be talking about. So here's what it is, right? You have the corrosion. If you look at the grid spans here, right? As you go up into the core, the temperature goes up, so that the corrosion goes up. Here's conventional zircular 4, here's improved zircular 4, and here's Zerlo for the same exposures, about a factor of 6 difference, right? So that if you have the same hydrogen pickup fraction, you have a lot more less here. The little ups and downs are due to the grid spacers that improve the heat conduction, and therefore the temperature gets slower. But anyway, you have this increase here, and what I'm trying to show here is that if you design a good alloy, you have a better chance of surviving. Now, the hydride particles, and I show them here, they are brittle, and they can degrade cladding ductility, ductility being the amount of energy that is absorbed upon fracture, and they will cause early fracture, depending also on their distribution. I'll just show an example here. So here is the oxide layer is shown here, and that's spalled away. So that the oxide layer is actually an insulating layer, and therefore the temperature here is colder than the temperature here, so the hydrogen just precipitates there and forms a blister. Now imagine that I'm trying to put a hoop stress in here. This would crack very, very early, and all the failure would concentrate here, and it would concentrate fail at a very small strain. So that's the kind of thing that we're worried about, the distribution of the hydrogen. So here's showing just quickly, this is again from the thesis of Adrien, it shows the hydrogen content against weight gain. Now let's assume that the hydrogen pickup fraction was constant, right? You would then follow one of these lines, 10%, 20%, 30%, 40%. Clearly it's not constant, right? It changes and actually increases, going from below 10% at the beginning to between 10 and 20 to about higher. And it also is consistently different for the alloys. The way that we have determined this is by testing, right? Painstaking work, right? You put the corrosion coupon, you test it out, measure the hydrogen, they put it again, measure it again, put it again, measure it again, for every one of those, right? And we managed to do this by 2 methods. One was using a destructive method with sister samples. I have several samples. I take one out, I measure it. The other way is to use prompt gamma neutron activation analysis, which is a very sensitive method of detecting hydrogen, which we did at NIST. And that one measurement fell right on top of the other. That was a very laborious process because we were testing it at Westinghouse. All the samples, measure it there, drive the samples back, put it in the corrosion autoclave, measure it again. It's just not a very easy process. But Adrian earned several PhDs on this. So the hydrogen pickup fraction is lower for aluminum alloys. And anyway, so what happens to the hydrogen once it gets in? It redistributes itself due to several laws. Fick's law, right, where it goes from high concentration to low concentration. The Sorey effect, it goes from high temperature to low temperature. And stress, and a gradient of stress, stress gradient. The region where there's a lot of stress, the hydrogen precipitate there. So how does it happen? What is the characteristic time? A characteristic time can consider it like this, a T equals L squared over 4D, where D is the diffusion coefficient and L is the length that you have to travel. And that's about an hour at the reactor temperature. So it's very fast. So it gets in, I have a temperature gradient, I can respond to that very fast. Let's say that the hydrogen is in here and it's all homogeneous, right? It's never homogeneous because I have a heat flux. So the temperature inside is higher than the temperature outside. But let's say that it was homogeneous, right? Now my oxide spalls off. So now suddenly this is cold. So then the hydrogen will now migrate in. And I'm saying that the response time would be very small. It would be at about an hour, which means that it would be much smaller than the normal exposure times that you have in the reactor, which is days or months or et cetera. So for all intents and purposes, we are more or less at the quasi-equilibrium all the time. We have axial and azimuthal gradients of hydrogen, and that's the project that I had with Maria and Kostadin and others at Michigan, where we were trying to couple the calculations from Cobra TF and from a reaction physics code to see how these variations in flux and in heat transfer could result in fluxes of hydrogen. So like this. So we have here, I put in here some of the students that have done this. Rob Dahm, this is in 2003. So this shows a hydride rim. So this is inside of the clad, this is the outside of the clad, and there's more hydrogen on the outside than on the inside, as you can see here. So this is a hydride rim. So this is radial redistribution, right? And then we have azimuthal when you have a differential along the azimuth. Well, so for example, the oxide spalling would be one, but I could also have, say, a corner rod where I have a greater heat transfer on this side than on that side. And I don't need very much. Something like 10 degrees difference will cause a big difference in the hydrogen content. Now, the acid profile, obviously, there's you know, as the temperature goes up, I have variations in the heat flux. And if I go and look at the interpellet region, right, I have a higher concentration of hydrogen there. Now, this is also showing, this is from a work that Mike Ballone did. This is showing hydrogen content as a function of the azimuth. This is showing as a function of 2 pi goes. So if I do the PIE, right, my overall, I took a ring like this, I measured this in a LECO system, I got about 600 ppm, but it might be 800 here and 400 here. So the 400, we don't care, but the 800 is what's going to cause failure, right? So it's the concentration. After a certain level of hydrogen in the clad, I mean, I can do a thought experiment. I have a pure zirconium lattice, right? I introduce an atom of hydrogen, introduce another, introduce another, introduce another. At some point, this is going to become another phase. I'm going to precipitate a second phase, and that's the hydrides. And the limit is expressed by the terminal solid solubility for precipitation and for dissolution, and this is what's called short. You can see them here. This is a metallography, and done by I am revealing the hydrides. And you're going to see that it looks very different at different scales. Very different from what you see there. What you can also put the matrix. People know about crystallography. The hydride is a delta hydride, which is FCC, and the 111 plane of the FCC is parallel to the 001 plane of the prevailing texture of Zirc is with the basal planes more or less this way. We also tend to precipitate more at the grain boundaries. You can see the different colors here show the different grains, and that the grains, the hydrides tend to precipitate along the boundaries. If I have a cold work material, it's like I have a stack of pancakes, and the grains are small in that direction, and they tend to be more horizontal. So I would precipitate preferentially there as well. We're trying to do some simulations of this to figure out what causes these very long. You know, if this is about 600 microns, this is, you know, several hundred microns here, right? So Pierre Clement and Mike Tonks at University of Florida, we're working together on an IRP project and trying to figure out using phase field modeling to show an optimal stack. And what Pierre Clement found is that if you put a hydride here, the optimal position for this guy is not on top, is not on the side, is not here, is not there, is not right there, like slightly offset, which kind of makes sense from the stacking that we see experimentally. Well, this is shown here, but just look at the solid curve. What that means is that if I have a hydrogen content of 100 ppm, I'm going to be precipitated at room temperature, precipitated. I get to the solid curve. the hydrides are dissolved. Above here, everything is in solid solution, right? Now let's say that I'm doing the opposite. I'm coming from high temperature and I'm cooling down the same sample with 100. I'm only going to precipitate at the dotted line. There's a hysteresis because it's not easy for the hydrides to nucleate. They'd have plastic deformation associated with the This hysteresis has always been known. This is what's called the TSSP, and this is what's called the TSSD, TSS dissolution, TSS precipitation. And only one of them is a thermodynamic limit. We believe it's the TSSD, not the TSSP, because it's a kinetic limit, and I'm going to show you how. And I'll show you why. So, whoops. So when we move the, I should have put this in an animation, but I didn't. So let me do that right now. Okay, as you can, I guess I was going to do it the other way. So, so when removing a fuel from wet storage to dry storage, you need to dry the fuel rod. You don't want the water in there, right? So to remove the moisture, it's necessary to heat the fuel rods. So this has caused all the hydrides that are precipitated to dissolve, right? When they reprecipitate again, they're going to reprecipitate under stress because the temperature is high and I have fission gases inside my clad, and now they're going to be a hoop stress. So what that does, instead of precipitating like this, they'll tend to precipitate in this direction. Stress. So the applied stress goes this way. Now look at these guys, right? I have here it looks like a bunch of platelets kind of stacked together. This one looks like a bunch. When you look at them closely, they are not like that. When you look at them in higher magnification, they are different than what it appears here, and I'll show you how. There is a critical stress that above which hydride reorientation can occur. If the stress is below the threshold stress, we do not reprecipitate in a reoriented fashion. So the way to check that, we took a tapered sample like this, right? A dog bone sample. I pull here, but then the cross section varies here, right? So for the single load, the stress is much higher here than here. And I have a gradient of stress. I can then do the experiment, and then I etch I cut it across this way, right? And then I check where I see reoriented hydrides, and I can calculate the stress at each place. In this case, I found that the critical stress is 150 megapascals. Beyond this, the hydrides are reoriented. Right? Now, this is an old picture from if you have a distribution of stress inside if you go from tensile to compressive and you have a line of no stress, the hydride precipitation, so it's tensile. Now look at this. When I blow up these guys here, this is what they look like. They look more like broken glass than what a deck of cards, and I'm going to talk about that in the next slide. This is the possibilities here, right? I could have a radiohydride that is a single hydride like this, or I could have a stacking of a deck of cards. The same orientation relationship that I had before, right? The hydrides are still plates that are still in the same direction, but they're not. Or it could be like this. And it turns out that it's not this, that it's not that, it's more like that, as you can see here. This is from the thesis of Nedim Chimbiz, that is in Oak Ridge now. To look at this, this is 5 microns here, you can see. Very detailed etching procedure that showed this much like that. This is what they call a broken glass trail. What causes this? What causes the fact that I can come up with an explanation maybe why it goes like this instead of going like that, but why do they stack up? Right? So there's some sympathetic precipitation going on. The presence of one hydride implies the precipitation of another, and this is kind of what we're investigating. When these hydrides form, then they have a very big effect on the cladding ductility. Here's a cladding fractography. This is with a liner, but forget the liner for a second. You can see that the crack propagated along the hydrides, right? The same here. The hydrides were horizontal, so it goes zigzag, 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 right? When the hydrides are more or less radial, it goes zoop, a lot more easy. This is a thesis of Rob Dahm a while ago. You can look at the hoop strain along, if you have a hydride layer thickness, rim thickness, and it basically, there's no ductility after about 100 microns. So the cladding ductility is severely reduced by hydrides, especially if the hydrides are localized or if I have a high biaxiality stress state. And this shows the fracture energy circumferential hydrides at low concentration, radial hydrides here. The ductile brittle transition temperature. You know, you go from low energy, which is brittle, to high energy, which is ductile, and you go in a very small temperature range. About 20 degrees, you change from completely brittle to completely ductile, right? We don't know why this happens. But we do know that it tends to happen at the higher temperature, which means it's more dangerous, than if you had lower, if you have circumferential hydrides. So, but we don't know what causes this, right? What's that?
What is the top line?
The top line is circumferential with low hydrogen content. So if basically has, right? So what we notice is if you do the fractography is that the hydrides crack at small strain. So this is tested at room temperature. This is tested at 300. Look at the hydrides here. And you create, you know, when you crack, they'll do this. You look at this. This is the fractured surface right here, and this is an uncracked hydride. One obviously cracked here, but there's a couple that crack here and here, right? And if you look at the circumferential hydrides, they have these little voids that are formed. And if I walk away from the fractured surface, I can determine what's the critical void nucleation strain that I can measure, right? Excuse me. I apologize. Let me put this on mute. Okay. So the other portion of the puzzle is what we call the hydride connectivity. And I define this in the following way. Suppose that I were an ant and I wanted to travel from here to here. And this was water, and I had these places here. How much water would I have to tread going from here to here, right? If I have, maybe I can jump from this one to this one, and I can jump from this one to this one if they're close enough, right? If they're far away like that, even though the coverage is about the same, I cannot do that. But if I have maybe some parallel, some circumferential hydrides like that, I can go zip, 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 and all the way through, right? So that's what we call the hydride connectivity. What is the fraction of the thickness that needs to be covered by this ductile failure? And that's what's going to control failure in the alloy, right? In the hydride. So it's really dependent on how much connected these hydrides are. And what turns out is that if I cycle the material several times, dissolve, reprecipitate, dissolve, precipitate, dissolve, reprecipitate, they get closer and closer packed. And this is what's shown here from the thesis of Kim Kolas. She did no cycles here. One cycle has a mixed, 2 cycles, and 4 cycles as it gets more and more concentrated. And I think that this is due to the sympathetic formation of hydride sympathetic nucleation. the hydrides are this way, 50% that way. Here. So we have studied this more closely using synchrotron radiation diffraction. This is traditionally studied using a process called differential scanning calorimetry. And basically, what I do is I heat two samples, and one of them has a hydride in it. So as I dissolve or I precipitate the hydrides, if it's an exothermic process, it will emit heat, and then I have to calibrate in order to make the temperature the two the same. I have to calibrate the heat in this sample so that and I can measure the heat of reaction that way. Well, in this, we can also do 80 kV. We can penetrate the thickness of the cladding. The cladding is about 0.6 millimeters. And I can give diffraction information on both the Zirc matrix and the hydride precipitates. Right? So I can perform experiments also while heating or cooling in a furnace, and also while I'm applying tensile load. I have a small X-ray beam with about 50 microns, which means that I can be placed at various locations in the sample. And it has very low background, as I'm going to show you, which means that I can detect small volume fractions of phases. So this is what the experiment looks like. The beam comes out of the board here, and I have the furnace here, and I have an Instron machine, this MTS machine here, the load frame, and I can pull this way as well, and the beam will come and right here is where the diffraction is collected. And so this is what happens, right? I turn it horizontally, but it's the same thing. So I have a dog bone sample here, and I have a high energy beam. I have diffraction patterns, both from the Zirc and from the hydride. And so the hydrides are traditionally like that, platelets like this, and an area detector, and I put temperature, and as the temperature goes up, the hydrides are going to dissolve, so that blue thing is gone. When that blue thing is gone, it means that the hydrides are dissolved, right? And then I cool it again. Maybe I cool it under stress, and I reprecipitate it here. And I can tell when the precipitation has occurred. So what happens, this is what the diffraction data is like, just rings like that, and I can index the rings to tell which phase I have. And then I integrate this, and I get diffraction pattern like that. And this is what the diffraction pattern looks like. Now, you all know that we have zirconium, chromium, iron precipitates in zircaloy, maybe. But it's a very small volume fraction, maybe 0.2, 0.5%. But you can see them pretty clearly here. If this is a log scale, right? If this was a lab X-ray machine, this would all be subsumed in the noise. So we have here is the Zirc peaks. There are these peaks here, boom, boom, boom. Then we have the precipitate peaks here, and these three peaks that are shown with the red arrows are the hydride peaks, the delta hydride peaks, right? And those we use to determine the volume fraction of the hydride. We actually use this peak here. And you can see that it's convoluted with another Zirc peak, but we use a sort of a technique to deconvolute those, a peak fitting scheme. This is the information that we can get. If we can deconvolute the two peaks, the peak integrated intensity is proportional to the volume fraction of the phase that I'm interested in, right? The peak position will tell me which phase I have, and the shift of that is going to tell me what elastic strain do I have on the phase studied, right? So if it's here, it's closed, and then a little bit this way, maybe it's tensile or compressive. And then the broadening of the peak gives me some idea of the crystallite size or the non-uniform strain that can contribute to peak broadening. So here is a typical experiment. We have integrated hydride peak intensity. So here's the temperature profile. Start at room temperature, go up, boop, boop. This is that height here. I have about 500, and then I cool down, right? So now I have a sample that has 500 weight ppm, let's say. So this is what the diffracted intensity looks like at the beginning. No change, no change, no change, no change. I start to dissolve. It's all dissolved here. Right? I keep on going. I'm increasing in temperature, have that flat top there, and then I start cooling, and then I start at this temperature, at this time here, I go whoop, and that's the precipitation again. If I now raise the temperatures, this temperature here is the dissolution temperature, and this is the precipitation temperature, right? And I can do that for several hydride contents. Here's another one, much lower one. I took it up in temperature, get it down, and here's my diffracted intensity goes to 0, blah, 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 0 up, go up there. And I got another one that says it's 390 and 248, okay? So now I have done this many times. I can now plot it against those curves, except that they are flipped, right? And you can see that the points agree very well with the differential scanning calorimetry for precipitation and for dissolution, okay? So we can study these things in situ. We can tell how things are going. And now the interesting thing is this. Going up here, right? If I'm in equilibrium, right? This is my concentration in solid solution. Boom, 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 boom. I keep on increasing with temperature, right? At some point, all my hydrogen is going to get out, so I don't have any more to increase, but I would follow this. If I do a little bit quickly, if I heat quickly, I would go a little bit lower. I'll go maybe here, okay? Because I haven't reached quite equilibrium yet. But let's say that I do that, and this solution happens pretty fast. No, so now I start cooling. I hit the precipitation temperature a little bit more. I start cooling down. I follow the precipitation curve. And that's what happened every time. Now, my student ever imagined, okay, what would happen if I stop here? Right? I shouldn't get any more precipitation because I have already precipitated what I had, but I might occur is that the hydrides might precipitate by not more nucleation, but I might precipitate by growth. And this is what would happen here. I would go all the way down to here. If he's correct, that means that this limit here is just a kinetic limit, and if I wait long enough, I get down to the solution temperature. So here's his data. So this is nucleation, and this is growth. Here's his data. So he took it up faster. So the thing was a little bit lower than that, but that doesn't really matter. It was all dissolved here. He comes here, and then he starts holding it at different temperatures, at 400, at 380, at 360, at 332, etc. And these are the data points. They all get down to the TSSD. They continue precipitating in the hysteresis region. They don't stop here. So this just controls nucleation, but this controls growth. Okay? And so the reason hysteresis, and this indicates that the TSSD is a real thermodynamic limit and the TSSP is a kinetic limit. Here's another point here. The reason for the hysteresis is this. He thought, well, what would happen if I didn't dissolve everything and I started cooling, right? So I go up here, I dissolve everything, I precipitate, I follow the precipitation curve. I go up to 3, I don't dissolve everything, and I start cooling. I start precipitating immediately. Instead of having a flat curve here until I hit the precipitation curve, instead of going from here to here, like what I see the top here, I will start going down immediately, which means that when the hydrides are present, precipitation happens immediately. Precipitation by growth. Hydrides, not nucleation of new ones. Okay? So this is a nucleation limit, and this is and here what we have is precipitation. And here he's just showing the same effect if I hold the temperature keeps going down because I keep growing, etc. So that's what this tells me is that the pre-existing hydrides facilitate additional hydride precipitation by hydride growth. So, questions for hydride-induced hydride storage safety. So here's the picture of the hydrides again, right? So I didn't put the scale here, but this is about 600 microns. So these guys are enormous. The grain size here is a few microns. So I have here. So I can't the same way. Well, it's not because they're trying to orient themselves to the crystal structure. And you can see that when I blow it up, it's still, a little wavy here. And maybe if I look at this about 100 microns, a grain size is maybe something really small here. So maybe they orient themselves. So this is, again, this is 10 microns here, and it's showing this is what these guys look when they're blown up. And you can see how they are really made of small segments. And these small segments can, maybe they follow grain boundaries, maybe they follow other things, and this is part of the things that we're investigating. But the other thing is, what causes hydride reorientation? We're saying, well, when you apply stress, the hydrides align themselves vertically. And I'm going, why? Why do they do that? There's no real particular reason why they should do that. You know that they form themselves in this way. They have this broken glass pile up here. Why don't they form here? Why don't they form here? Why do they form right on top of each other? Some people have said, well, it's the dislocations that they are present. Some people say it's the elastic strain around them. Some people say whatever, but they don't do this when there's no stress applied. Now, when we have tried to do what's called phase field modeling and apply stress to it, but maybe because our phase field models are not sophisticated enough, we haven't yet been able to reproduce the reorientation of the hydrides even with very, very high stresses. It may be because we're doing this problem in 2D instead of 3D, and maybe we need the other stress components in it. Maybe we need to have deformation. But that's part of the things that we are trying to study right now in this process. So the conclusion is this, is that the hydride picked up by nuclear fuel cladding is driven by concentration, temperature, stress gradients, and can create weak spots. I think I demonstrated that. The fate is primarily governed by the hydride distribution, and if we have hydride microstructures that are harmful, like reoriented hydrides, is a concern. And this is a specific concern for storage of fuel. So we are addressing that in this IRP project, which we have one of our partners here, Mohammed Zikri, in the back there. You can see it. Westinghouse, Los Alamos, Oak Ridge, Queen's University in the UK. And we have several subtasks in here for hydrogen migration redistribution. What I mainly talked about was the second part here. And then we have the third part, which has also certainty quantification, implementation, benchmarking in the codes. And we plan to be doing more of that over the next few years, doing some critical experiments that can give us some insight so we can understand what would be a safe dry storage procedure that would not cause the cladding to become brittle. So that's, I think, all I got. Thank you. Be happy to take any questions.
Yes, questions and comments.
How does radiation field affect?
I don't know. That's an easy question. So radiation is going to increase the hardness of the matrix. For one thing, it might have a different precipitation of the hydrides. It's very difficult to separate what is the specific effect of radiation with the other things that happen in the core. For example, the fact that I have a temperature gradient, the fact that I may have stresses applied, all these other things. But I don't know the answer to your question. I mean, what we have is complicated enough.
Yes, at high stresses, is it possible for these hydrides to form below the terminal?
Okay, so let me get back to your question here. So let's say that I have this curve here, right? You're saying if I am where? If I'm here?
Yeah, below the solid solubility.
And I have precipitation induced by the Okay, so what I've seen, and I haven't talked about that here, is Evrar also tested for what is the TSSP for reoriented hydrides and for non-reoriented hydrides. So under no stress, this is what happens. Under stress, it actually goes here. You need to have more undercooling in order to precipitate. So it seems to work the other way. Yeah.
During the reorientation of hydride, do you think if, the point defects will play some role in that process?
I'm sure. Not only the point defects, but also the line defects, all the defects.
Yeah, but I'm thinking there or line some.
What is your question again?
A question. I mean, over this process, is there some?
So the one thing I didn't mention is that the hydrides have a higher specific molar volume than the matrix. So they want to occupy a bigger volume. So they tend to deform the matrix and form dislocation, precipitation. The point effects that you're talking about, you mean for under radiation, right? So they might come and relax some of these. So if, for example, the hydride is a sink for vacancies, let's say, because it's, you know, burning. People talk, I think just Ken Russell mentioned that if you had precipitation under radiation and the volume of the precipitate is bigger than the matrix, that the vacancy flux to it could make the precipitation easier, relieve some of the stresses. This is a bit speculation because I need to have a net flux of those defects into there, so I need to have a net flux of interstitials somewhere else. So what I would say is I don't know.
Other questions?
Yeah.
Are there ways to completely reorientate the hydrides? Like if you cool it down very severely, very abruptly, so what do you know what will happen?
So if you think about what actually happens in a cooling situation, right? I have this fuel assembly that I'm heating up, and I have to cool down. And I would like to cool down more quickly, but I can't really do that because how am I going to do that? So actually the cool down time is something like 24 hours. So it's not really practical that way. There might be other concerns. So let's say that I can't do it. I can't dip it in water because the whole purpose of the drawing was to take out the water. But a fan, I don't know. I mean, it's hard. And this is very active material, right? So I don't want to be playing around with it. But you know, I think the thing to do is to investigate the areas at which this phenomenon would be of interest. So what would be the consequence of this, right? Let's say that I have radiohydrides in my sample. What would be the issue? Well, if I dropped one of those canisters, right, the fuel might shatter. Do I care? Maybe I don't. Maybe I don't care. Maybe I say, okay, if it happens, I'll deal with it when it comes, and it's enclosed in the canister anyway, blah, 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 etc. But if I care, if I think that I need to keep the fuel integer inside the canister, then I need to figure out up to what temperature can I heat without causing a problem.
Other questions?
So can you comment on the look that NRC has on hydriding?
Yeah, so this work was funded by the NRC. The work that Patrick did was funded by that, and so I think the NRC's, well, I don't think the funded the work was Bob Eisinger, and he now has left the NRC to go somewhere else. But I think in the meantime, this approach, I don't know what you know in terms of the actual procedures for drying and everything. I'm not sure if they have come up with some guidelines yet, but we are trying to, you know, provide the data they can understand.
I was thinking more of the fact that NRC has been limiting the lifetime of the cladding based on the oxide.
Well, it shouldn't be the oxide. It should be the hydride. Yeah, and you know when Ralph Meyer was doing the stuff for the RIA, he started, well, okay, first is burn up. There's not really burn up because I could have a better alloy that is not going to have as much corrosion. But it's not really corrosion. It's really the hydride. So if I could have the same corrosion thickness, but with a lower hydrogen pickup fraction, I'm good. I'm fine. So I designed an alloy like M5 that has very low corrosion and very low hydrogen pickup. It's better, right? As I showed you the difference between Zerlo and the Zircaloy 4, right? That's, it's better. And you want to have the best alloy you can possibly have. But given that most of the fuel that is in the inventory now is not idealized stuff, there's stuff that has oxide spallation, there's stuff that has whatever else, you have to deal with reality, right? Oh, okay. Thank you. Very nice. Thank you very much. The fixed smile.
Yes.
Thank you very much.
There is something else.
Oh, yeah.
NC State.